revolution that was brought about when twistor theory was introduced. And now, furthermore, one of the applications, we can now investigate correlation functions directly in momentum space, where many of the physical properties, including unitarity and causality, are most easily applied. And we can now have an S-matrix bootstrap program, much like the one for CFT. An S-matrix bootstrap program because it involves massive particle, and this will be relevant for the spectrum of large yin-yang mills and, for example, for the predictive completion of gravity. Now, finally, for massless interactions, I've discussed that it's actually it's fully constrained by a soft theorem, which really reveals the underlying structure of the UV theory. But it also tells you more. If you find any new soft theorems that are outside of what I just discussed, that implies that maybe there's some new hidden symmetries that are unaccounted for. And indeed, this is one of the papers that I did with my students after the second year that I got here, which we found, besides the soft theorems that I discussed, which I know what the symmetry is, we found in particular theories for supergravity, for example, that we find there's new soft theorems that are there, which we have no symmetry, at least so far, no symmetry interpretation for it. And so this is just an example where there may still be many potential hidden symmetries that are not known that you can only uncover using soft theorems. Now, since this is a promotion talk, I think I should, so this is the talk I talked about is about the two upcoming work that I should publish. That should come up this month. It's really built on a series, these work which I did since I came to NTU in 2014. And the red highlight are peoples and our members in the NTU physics group. So Wei-Ming Cheng is a graduate student of mine who graduated and is now in UCLA. And there's Dao, who was a research assistant in his last year. And we also did, so some of the soft theorem analysis was actually done with him. And so I'm really very grateful for the support that I have from the department, and really have a wonderful class of students that I work with. Here, these are the students that have already graduated. I have not listed the students who are currently now working with me, and just where they've gone to. I didn't know that there was a rocket company in Taiwan. And this is their publications, and yes. So, thank you very much.
Now you can ask some questions to Professor Huang. Any questions? Okay, Inami-san.
The statement you made toward the end of your talk, is it independent of the basic theories, UV renormalizable or non-renormalizable?
Which part?
No, about soft theorems of that kind.
Right, it's independent of what the UV completion is, so that means that it's independent of what, that means it has to be renormalizable, right? If it's a UV completion, it has to be renormalizable. Yes. So, in other words, it's telling us what is the renormalizable theory, the structure of the renormalizable theory in the UV. So that's why I really want to use the string amplitude to show as an example. You have a string amplitude and you don't know what the complete theory is. Just by looking at these soft behaviors, you see the presence of the D brane directly in your face just by looking at it. It's telling you that you're breaking translation symmetry. This theory is breaking translation symmetry.
Okay, status?
So it's very, very nice talk. So we know from the pion physics, we know that if we consider this, as you said, this spontaneous symmetry breaking, etc., which is actually not spontaneous, but it's actually broken in the pion case. But okay, you can assume SU2 is approximately okay.
Yeah.
We don't need to know the theory that causes the symmetry to break, etc. We can use this theory of spontaneous symmetry breaking and study how the pions interact and get the pion, for example, momentum to zero and get the interaction to zero. And this is enough for us to study what's happening without knowing the underlying, the theory actually that breaks, that is QCD or whatever. In your case, I think that's how I understand the pion.
Yeah, that's correct.
So in your case, now you go one step further and you say that by studying these pions or Higgses or whatever they are, that may be Goldstone bosons of a space-time symmetry breaking, and I get the momentum, for example, to 0, and I have this residual term, I can tell that the difference, that here I don't have an SU2, I don't SU something.
Exactly, that's the statement here. So the statement is that if your breaking is not, because if it's space-time symmetry breaking, for example, if it's translation symmetry breaking, then the leading term will also be 0. As you see, there was also 0, exactly like the pion, that the usual pion with the SU2.
But you have a residual.
Right. But by looking at the residual, you actually pick out that this is actually not a SU2 pion in the UV, it's actually a space-time symmetry breaking.
So experimentally, we should.
Yes.
So somehow this enters the
No,
experiment.
yeah, this is a prediction of
It's a prediction.
yeah, and I've used explicit model, which I know is a spacer, to show that indeed these are the terms that arises.
I mean, in the Higgs case, there are many models that have it as a constant. So.
Yeah, so that's why I frame this as related to answering the question of why mass is small.
Okay, any more? So I have a simple question. So in your application part, that you say is G minus 2, you know, in the QCD calculation is very, very complicated.
Yeah.
And a lot of heroic effort has been made.
Well, this is really for electroweak. The thing that we were computing was the electroweak.
But, okay. Have you just tried and compare your results with the?
Well, the electroweak we tried. I mean, so we compute the electroweak and we compare with the 1993 paper. It was a couple of pages long. But yeah, so I mean, one of the hope is, of course, as you know, that one of the next frontiers would be precision Higgs, and which now electroweak processes are extremely, NNL electroweak processes are important. Of course, really the roadblock is really the massive integrals, how to do the massive integrals, not really constructing the integral, but the massive integrals, how to do. But we're hoping that this might have some help in that direction.
So your G minus 2 example, it seems that you don't need to loop. You don't need it to loop. You just put the system together, that's all.
Well, no, I put it together because I just taught the course, so I'm still very familiar with how we do. In the usual case, you have to loop integrate, right?
Yes.
And then you need to Feynman parameterize it. And after the Feynman parameterization, then you separate out the piece that was the magnetic moment. After this, if it was originally in the loop integral, it's hard to disentangle the piece. Here, what is different is that in the get-go, the loop that you constructed, the two pieces are already separated. So as I mentioned here, these two pieces are so this is just the gluing of these three tree amplitudes together to form the loop. After you glue it together, because this is really because it is on shell and there's no redundancy. So the magnetic moment already comes out very cleanly separated in these two terms, which is these two terms that you write here, and then you just convert it into a single loop part. And then you just integrate
You still have to do this loop.
yeah, but the difference is that in the usual case, you have to do the loop in order to do the separation.
You know, the computer can help us.
And here, this is before you're doing the loop. You already know that, or in other words, you already know that the magnetic anomalous moment is not 0, just by constructing because it's already cleanly separated.
Okay, any more? If not, let's thank Professor Huang.
Okay, thank you very much.
For students who do not sign the class,